So this is Professor Ogilvie from an extraordinarily distinguished university in the U.S. And he will be speaking on QCD at finite density.
Actually, the reason I came here was so that I could see Carl. No. So one of the pieces of advice that I got a lot as I was maturing as a physicist was to always start a talk at the very beginning. And so that's what I'm going to do here, because Jerusalem is a very good place to start at the very beginning. So let's see. Yes, this is in the beginning. Breshit bara Elohim et hashamayim ve'et haaretz. In the beginning, God created the heavens and the earth. Unfortunately, it turns out that the first day of creation is at a very high energy scale, and it's not currently accessible to us experimentally. And so really, what we have to do is we have to go to somewhere around the fourth day of creation. That's when there was light to rule the day and the lesser light to rule the night. Sometime around then, is lower energy scale, more accessible to us.
Separation of radiation and matter.
Yeah, exactly. Yeah, the recombination era, roughly, fourth day. But, it's not enough just to have a description of what's going on. We also want to know exactly how things developed in the early universe. Here's one theory. And God separated the light from the dark.
The microphone, because you're
We
recording.
need the mic.
Where's the mic?
I've got the mic.
Okay.
I am the mic. So we want to understand mechanisms. Here's one, but that's probably not the best explanation. So, let me start here. So this is, in terms of our ability to understand the early universe and related phenomena today, what we're really talking about is roughly the scale of QCD, which is an extraordinarily complicated system. This is the phase diagram of QCD as a function of temperature and baryon density. And, the first day of creation is somewhere way up here, and we're somewhere down here, okay? At finite, some non-zero baryon density. So this is the hadronic phase of QCD, in which red, green, and blue colored quarks are confined to form hadrons, strongly interacting bound states, mesons and baryons. And then up here in temperature is the quark-gluon plasma. And over here, neutron stars and maybe various exotic forms of matter that we don't understand completely yet. Experimentally, the primary region that's been probed experimentally by Rick, the relativistic heavy ion collider at Brookhaven National Labs on Long Island in the US, is this blue piece. The LHC has a heavy ion program, ALICE, which is going to be at somewhat lower chemical potential or baryon density, but somewhat higher temperatures, okay? And there have been some, the experimentalists call them scans in this region here. So the main feature that we see in the phase diagram is that there's a line of first order transitions that separates a low density phase from a high density phase, and there is a critical endpoint right here, okay? Or I should say not right here because we actually don't know where it is. There is a lot of interest in this critical endpoint. In fact, there's a regular meeting called CEP for critical endpoint that's just devoted to the critical endpoint.
What is the order of magnitude of the temperature?
The order of magnitude of the temperatures, this is about 140 MeV, okay? And this is about what you think it is. Call it a JEV in nice round numbers. Because, this is the transition from normal nuclear matter to collapsed matter. And I'm going to show a second phase diagram in just a second. I'm going to tell you more details about it. Okay, so this is the same phase diagram, except here it's explicitly in terms of baryon chemical potential rather than density, but they're essentially the same, and temperature here, okay? And, this shows you all the possibilities. This is the hadronic vacuum, the confining chiral symmetry broken vacuum of QCD. This is a crossover rather than a phase transition. This is where we go from confined quarks with chiral symmetry breaking, the formation of a fermion-antifermion condensate, to the quark-gluon plasma phase. Presumably out here, we know that the large density phase of QCD at very low temperatures is a so-called color flavor locked phase. But we don't really have a good understanding of this regime at all for reasons that I'll come to, okay? So, Alice at the LHC here, Rick here, and then there's this very interesting area in here which nature has not explored for us, basically moving diagonally in the temperature chemical potential plane. And although nature has not explored it for us, there is an experiment at FAIR in Germany called CBM, compressed baryon matter, and that is going to explore this region. And I'll come back to that at the very end, as you'll see. Okay? So that's the phase diagram that we have to work with. This actually summarizes a tremendous amount of work over several decades. A lot of the work of our information theoretically at mu equals 0 comes from lattice QCD studies, okay? But we do not know as nearly as much about this region here in finite chemical potential because of the sign problem of QCD. QCD is one of the class of problems where there is a complex weight in the path integral. In fact, it is a generalized PT symmetric problem, as I will explain to you. Okay, so this is one slide on the essentials of QCD at finite temperature and density. The idea is that we're in Euclidean space-time with periodic boundary conditions. So we're studying trace e to the minus beta h, so the trace gives us periodic boundary conditions. And Euclidean time, beta is 1 over the temperature. So here's Euclidean time and space. And in gauge theories, particles, when, just imagine a fat, stupid, dumb particle just lying there in space, and it's just sitting there and moving along in Euclidean time. And by virtue of moving in Euclidean time, it picks up a non-abelian phase factor, the Poliakoff loop or the Wilson line. And this is what it is, okay? It's just a generalized Aharonov-Bohm phase factor that's associated with the non-abelian degrees of freedom. So A4 is the time direction of A4. This is actually a 3 by 3 matrix. So this is a 3 by 3 matrix as well. It's path ordered, and it's just exactly what you think it is. This Poliakoff loop is the autoparameter for the confinement-deconfinement transition in pure gauge theories, and it's related to the free energy for inserting a heavy quark into the system. So if I had a system that was in equilibrium and I wanted to insert an extra heavy quark into it, the effect of inserting the heavy quark would be to insert the phase factor associated with this operator. So the expectation value of this operator is in fact related to the free energy required to insert a heavy quark. Yeah, Conrad?
Just a little question. Is this the same like in Wilson loop?
What?
Is like a Wilson loop?
It's a kind of Wilson loop, yes, but it's one that takes advantage of the periodic boundary conditions at finite temperature. So it's sometimes called the Wilson line, because you see it closes on itself by virtue of the fact that by virtue of the periodic boundary conditions. So it's a special kind of Wilson loop. Okay, and this is the trace of p dagger, which is associated with heavy antiquarks. And at zero chemical potential, of course, these are the same. But once you start including the effects of a non-zero chemical potential, these should not be the same because we're not treating quarks and antiquarks in exactly the same way. In fact, what a chemical potential does, and this is very similar, in fact, to some of the issues that Naomichi talked about earlier today, the chemical potential favors particles over antiparticles by a factor of e to the plus beta mu for particles versus e to the minus beta mu for particles. And so if you have a particle going around, it receives a weight in the path integral of e to the beta mu, but an antiparticle goes the other way, and it gets an e to the minus beta mu. And it is precisely this effect that leads to a non-Hermitian behavior of QCD at finite density, because you are weighting contributions of P differently from contributions of P dagger. And we'll see that explicitly in just a minute. Okay, so I'm going to show you a zero-dimensional example, okay? And most of the issues that we'll see, most of the theoretical issues that we'll see later are all here, okay? So I should have said at the beginning that this is work done with Hiromichi Nishimura, currently a postdoc at Bielefeld, a former student, and Kamal Panjini, currently a graduate student at Washington University. This d equals 0 example was first studied by Arts and Stamatescu some time ago. And the idea is this. We have a zero-dimensional action, okay, in which the variable we're going to integrate over is this angle theta. And it looks like a cosine, except I've shifted theta by an explicitly imaginary term. And you should think of this quantity mu as being a dimensionless chemical potential, which is why I chose mu. And of course, I can also write this in this form. This action is invariant under an antilinear symmetry, which consists of two symmetry operations, neither one of which is a symmetry of S, but the combined action of C and K is in fact a symmetry. C takes theta to minus theta. Think of it as charge conjugation. K takes I to minus I. This is ordinary complex conjugation in Euclidean space. And what we're going to do is we're going to compute a partition function and associated expectation values by just integrating over theta, just like so. Okay? Now, in fact, you can do a strong coupling expansion in J, and you can find out that the partition function is exactly a modified Bessel function and is in fact independent of mu. So this is a model that's exactly solvable by a strong coupling, or you can solve it exactly by other methods, including contour deformation, which is what I'm going to do. So I'm going to introduce z equals e to the I theta. I'm going to change my contour from the unit circle to another circle that also encloses the origin. And I can solve analytically for all the expectation values I want by this method. And what I'm really doing, if you like, is I'm noticing the fact that there is a complex saddle point of the action. And I'm changing my contour so that it actually runs through that complex saddle point. If I tried to expand around a real value of theta, which is something that's been actually tried a lot, then you would get incorrect answers. And you see that even though the partition function is independent of mu, expectation values, this is the analog in this the Poliakoff loop in this little zero-dimensional model. And you see it explicitly depends on mu. And this is the analog of p dagger, trace p dagger, and it explicitly depends on mu. And they're different, okay? And so we're going to see this all over again and again as we proceed towards a more phenomenological description. Okay? Now, this is the last slide that you actually have to stay awake for. So those of you who are falling asleep, please wake up for this. Then, you know, we'll come in. I know this is late in the day. Some of us are jet lagged. But what we'll do is I'll go through an enormous amount of interesting technology and phenomenology. And at the end, I'll come back to the phase diagrams that we started, and I'll show you why PT symmetry is important, potentially, to the physics of finite density QCD. So you just have to pay attention to this one slide, then you can sort of become torporous again. Okay? So this is a generalization of the zero-dimensional model, and I was very lucky that Haitano gave his talk before mine, because this is actually kind of a similar model. If you think of a one-dimensional model, you know, 1 plus 1, so this is finite temperature, and instead of a box, you think of a line, okay? Then you can imagine this model on a line, or if you want to imagine this is spatial boxes, three-dimensional space-time, you can do that too. But the point is that the Poliakoff lines, the Wilson lines, interact with each other. And in strong coupling lattice gauge theory, you can actually determine analytically the approximate effective action associated with these effects. So this is a result from strong coupling lattice QCD, which we understand very, very well. There's a nearest neighbor interaction between trace P and trace P dagger on adjacent sites. This is induced by the gluons. And then if I have, say, static quarks, very heavy quarks, that are not moving in space, only in time, then they contribute terms like this, okay? And I'm not going to derive this, but this is essentially the fermion determinant associated with the quarks, and this is the fermion determinant associated with the antiquarks. There's a factor of, oops, where'd I go? There's a factor of e to the beta mu minus beta m, where m is the mass of the quarks, associated with the quarks. And then a similar factor, but much smaller, associated with the antiquarks. They're heavily suppressed by finite density. Okay? And so this is a nice model because I can essentially solve it analytically in 1 plus 1 dimension. And that also gives me the strong coupling solution in higher dimensions. Now, this is just one slide. And it's not the main focus of what I'm going to tell you, but in some sense it bridges an important conceptual gap between what I'm going to talk about later and the zero-dimensional model. Joshua.
Just to get oriented, Schwinger model in one dimension is also confining for the obvious reason that...
Right.
So if I just use the Billian gauge theory, what would I get here?
I'm going to talk about that, oddly enough. Yeah, in just a minute, just 1 minute. Okay? So if I turn off, so this is in fact the spectrum of the transfer matrix associated with this action in 1 plus 1 dimension. I've normalized the eigenvalues so that, first of all, what I've done is I've turned off the antiquarks completely, because you see they're very heavily suppressed. And the lower axis here is just Z1. And I've normalized the energy eigenvalues, well, they're not energy eigenvalues, the eigenvalues of the transfer matrix in such a way that if you look at this Mathematica, can't live with it, can't live without it. Okay, so this is 1 here. And this number here at z1 equals 0 is 4/3, which is exactly the Casimir invariant of the fundamental representation of QCD. Okay? So this is a free theory. It's a trivial theory, both in the continuum and on the lattice. And what Joshua asked was, what happens if I turn off the Quarks effects? And the answer is that you get a series of eigenvalues that are proportional to the Casimir invariant of each representation. So for example, this is the fundamental. This is at exactly 3 at z1 equals 0 is the octet. This is the 6 and the 6 bar, right? And what you see in the transfer matrix is that for any value from z equals 0, you see that there are two degenerate eigenvalues because I'm plotting the real part, as we're used to. But that as I increase z, the two eigenvalues separate, meaning they both become real instead of a degenerate pair. And the octet, which actually is a real representation, just stays real. But the 6 and the 6 bar split up around here. So what you're seeing is the familiar phenomenon of PT symmetry breaking. Okay? So here PT symmetry is broken. Here it's unbroken in these lower eigenvalues. But you see the phase structure is actually very, very complicated. I only plotted a few of the lowest lying eigenvalues. Okay? So this is an indication that 1 plus 1 dimensional QCD shows PT symmetry and PT symmetry breaking, and that it will also occur in any dimension in the strong coupling limit of the lattice QCD. Okay?
It's essentially what happens at the site, single site. You don't really care about dimension much.
Yeah. I mean, it's a very local theory, you know. But you know, I can't do strong coupling in the continuum, right? And so when I go to the continuum and when I want to make contact with experiment, I have much less in the way of controlled analytical tools. For example, we lack any controlled analytic understanding of quark confinement. We lack any controlled understanding of chiral symmetry breaking. We lack any controlled understanding of color superconductivity. So in order to make progress, I have to move away from, you know, happy simple models and look at things which are very, very complicated models ultimately. Okay? So that's how things work in you know, simple cases. So let me just tell you about the general formalism for this generalized PT symmetry in QCD. Okay? So QCD at zero chemical potential is invariant under charge conjugation, and it's invariant under complex conjugation. Okay? But once you introduce a finite, a non-zero chemical potential, charge conjugation is no longer a good symmetry because, of course, I've filled space with some finite density of color-charged particles. So charge conjugation symmetry is explicitly broken. So charge conjugation is no longer good symmetry, but CK actually is. So the way you see this, in the simplest possible way, I think, is that charge conjugation acts on the gauge fields. First of all, they pick up a minus sign. That's the usual minus sign of, you know, say QED. But because they're not abelian gauge fields, they also pick up a transpose or a star, their equivalent. And that's things like turning a W plus into a W minus. That's what the transpose does in the case of SU2. And that generalizes to SUN. And then, of course, K just turns I into minus I. And so if you look at this Poliakoff Loop guy, you see that CK turns P into P because the I and the minus I cancels out, and the transpose turns out to be harmless because we're always taking traces. And from this fundamental result, you can derive this result from CK symmetry. It was originally derived using gamma matrix techniques, but it actually follows from this symmetry. and it's a generalized PT symmetry. And so what we want to do is we want to explore the consequences of PT symmetry in finite density QCD. Okay? So I'm going to go back to that zero-dimensional example I showed you, and I'm going to say, well, let's think about what a saddle point approximation would look like. And so if I think about the Poliakoff loop in Poliakoff gauge, right, where the eigenvalues of P are time-independent and diagonal, you see that I can write the unitary matrix P as a set of 3 eigenvalues. But of course, I'm constrained by unitarity, and I'm also constrained by charge conjugation invariance. And you can show, as here, that there's a unique set of eigenvalues that should be relevant or dominant at mu equals 0. And they just look like this. There's 0 plus theta and minus theta. And if you choose theta equals 2 pi over 3, that is, the eigenvalues are uniformly spaced on the unit circle, then trace P is equal to 0. This is what we usually associate with the confined phase of QCD, because this says that the free energy to insert a heavy quark is exactly infinity. Okay? And then the deconfined phase, the very high temperature phase, the eigenvalues move, and they all move towards 0, and then you get trace P equals 3. That's the maximum value in the very high temperature limit. Now, the problem with this is with this parameterization, trace P is always equal to trace P dagger. And on physical grounds, we know that we should be treating the quarks and the antiquarks differently. They should have a different free energy associated with quarks versus antiquarks. So what we have to do is generalize this understanding and move into the complex plane. And when we do that, and we require invariance under this generalized PT invariance here, we find out that the requirements are that the eigenvalues, if Zj is an eigenvalue, this is general for SUN, then minus Zj star also has to be an eigenvalue as well. And if you look at this for SU3, there's a unique parameterization where instead of having theta minus theta 0, we have theta minus I psi minus theta minus I psi plus 2 I psi. And this is unique. Okay? This is the unique set of eigenvalues which are invariant under CK. Okay? So now we know what a saddle point should look like, should one exist. And we see that trace P has this form, and trace P dagger has this form, and they're not the same anymore. As long as psi is non-zero, trace P and trace P dagger will have different values at the saddle point. Okay? That's what we want. So, all good. Everybody okay? Or sleep? Sleep's fine. So, if I do a perturbative calculation, say of the effective potential associated with the Poliakoff loop or the Wilson line, you get terms that look like this, okay? So this is really just the finite temperature effective potential, or if you like, the free energy. If I set the Poliakoff loop equal to the identity, then this would be exactly the expression that you're used to for a relativistic gas of fermions, at finite temperature and finite density, okay? But if you take into account the idea that the quarks are moving in a non-trivial Poliakoff loop background, then it turns out that you have to insert this factor of P, and you have to take the trace over the SU3 degrees of freedom. So an elementary finite temperature field theory calculation. And this can be evaluated analytically. It is somewhat non-trivial when the eigenvalues are complex, but following these guys, we were able to do it. And in general, you know, if you had complex eigenvalues associated with P, you'd expect to get a complex expression, right? But PT symmetry comes to the rescue for you, and it turns out that when you plug in a PT symmetric or CK symmetric background Poliakoff loop and explicitly evaluate the effective potential, the imaginary terms disappear, and at the saddle point, the free energy or the effective potential is real, right? So it's doing exactly what we want. In terms of formalism, if you look at the first derivative of an effective potential, and you say, well, what's going on here? What do these theta and psi actually represent? Then you realize that what we're really doing is we're decomposing a diagonal SU3 matrix, A4 over T, into theta times something that's proportional to lambda 3 minus I psi times something that's proportional to lambda 8. And if we look at the consequences of a particular point being a saddle, and we differentiate with respect to theta, and we differentiate with respect to psi, it turns out that you can prove that because of the way the Poliakoff loop couples to quark densities, that this one says red minus green density is 0. In other words, the number of red quarks equals the number of green quarks. And differentiating with respect to psi says number of red plus number of green minus twice the number of blue is equal to 0. And so the conclusion is that the CK symmetric saddle point is a color neutral saddle point. Again, this is not something you all would necessarily appreciate, but it's something that has actually plagued attempts to do analytic calculations in the past.
This is weak coupling. We are coming from the side of the weak coupling.
Yeah. Well, no, I mean, no, actually it's not. All I've assumed is that there is some effective potential. There's no, at this stage, you're right, I'm going to have to make assumptions out the wazoo in just a minute, but so far this has just been completely general. I just assume there is an effective potential.
Why is the no term proportional to the unit matrix in A4?
I'm sorry?
Why is the no term proportional to the unit matrix?
Because it's SU3, not SU3 cross U1.
It's not U3, it's just SU3.
If I had something that coupled, if I had a gauge field that coupled to baryon number, that would be 1, 1, 1.
Yes.
But I don't have a gauge field that couples to baryon number.
But then this argument.
Don't want it, otherwise the Earth and the Moon would.
Correct. It does not work, and that's a well-known feature. But in fact, we know that there is no gauge field that couples, as near as we can tell, to baryon number. Okay. Now again, just being completely theoretical and general here. The mass matrix is not Hermitian anymore because the theory is not Hermitian. You can see that explicitly. I'm going to calculate the mass matrix associated with this theory, okay? And it's this, and you see the I's, and you can check explicitly that this is in fact not a Hermitian matrix, right? But it is a CK symmetric matrix. It inherits the CK symmetric properties of the saddle point. And the general form of this will be that if you calculate these mass eigenvalues here, they will have this general form. And here I am using I'm assuming a little bit about perturbation theory here, but it hardly matters. You see that there will be the possibility of getting a term under square roots, which could be negative, and therefore we will get complex conjugate pairs under some circumstances. Now, I'll just tell you that if you look at this in the high temperature, high density limit, that's known. It's a one-loop calculation. And the answer for this expression will reduce down to this. And that's the familiar result for the so-called Debye screening mass associated with QCD at high temperature and density. Okay? So the mass matrix will either have two real eigenvalues or a complex eigenvalue pair. And so one of the questions we're going to be interested in is, where does QCD break PT symmetry? Where is there a complex eigenvalue pair? Where are there two real eigenvalues? Okay, so now I transition to unabashed phenomenology, okay? Because I don't have a fundamental theory of confinement. I don't have a fundamental theory of chiral symmetry breaking and chiral symmetry restoration. But in fact, we do know an awful lot about building phenomenological models that incorporate this. And in fact, in this set of recent papers, we considered 6 models. One was not enough. We considered the case of massless quarks with no chiral symmetry breaking. So these are massless quarks. This is the easiest case. We also considered the case of very heavy quarks. So chiral symmetry is explicitly broken. This has a very, very different phase structure from QCD. And so it was important to us to understand this and see that we were really understanding very general phenomena before we moved on to the most difficult case, which is, and the most realistic case, which is the so-called PNJL, or Poliakoff-Nambu-Yonah-Lacinio models. These are state-of-the-art phenomenological models that include confinement effects at finite temperature. They include chiral symmetry breaking effects at finite temperature. They reproduce a lot of the behavior of QCD at 0 temperature, including spectral properties, and a lot of the behavior known from lattice QCD at finite temperature. Okay, again, finite density is much less known because we do not have good lattice simulations because of the sign problem. And that's the most difficult case because we are trying to minimize the free energy or the effective potential as a function of theta and psi, the two variables I introduced before, but also in terms of the chiral condensate psi bar psi. Okay? In each case, we considered 2 different models of confinement, Model A and Model B. They're both phenomenologically motivated models of terms we can add to the effective potential that will give us a good description of what we know at finite temperature from lattice gauge theory. Okay? These are the models. This is how they look. The effective potential is a gluonic term, a quark term, and then a deformation term, let's call it, or a confining term that will give us confinement at low temperatures and deconfinement at high temperatures. The gauge boson contribution is taken from one-loop physics, which we know is the correct description of the high temperature behavior of QCD. The deformation term will be taken to be either Model A or Model B. In the form I've given them, they look very similar. You may know that this is given in terms of B4, the 4th order Bessel polynomial. This can be given analytically in terms, this one can be given analytically in terms of B2. This one is sort of like B0, or I guess B1. And they're both given in terms of the adjoint trace rather than the fundamental trace of the Poliakoff loop here. So if you think in terms of a winding in round the lattice, what's happening is the gluons go around the lattice, and the n equals 1 term corresponds to going around the lattice once in the time direction, the n equals 2 term twice, 3, 4, 5, 6. Very physical understanding of what these terms are doing. I can also write model A and model B in more analytically tractable forms. Here's B2 as promised in terms of the differences of the eigenvalues here. And here's model B, which is, if you're familiar with random matrix theory, it should look familiar because what it actually represents is, aside from some factors in front, it represents the log of Haar measure in a diagonal gauge.
Spread evenly.
Exactly. What it does is it actually enforces the Z-n symmetry of the underlying gauge theory by making the eigenvalues repel so they're uniformly distributed around the unit circle. You're exactly right. So if you look at the pure gauge theory, which is where the input comes from, we know that the pure gauge theory has a deconfinement phase transition, a first order transition, at 270 MeV. This is not from experiment, it's from lattice gauge theory. And if I fit T versus TC, and I look at the most sensitive thing I can measure thermodynamically, which is delta, this is the so-called interaction measure. It's 1 over T to the fourth times the trace of T mu mu. Okay? It's essentially the dimensionless trace of the energy momentum tensor. Okay? And it's essentially 0 below the transition. It's essentially 0 at high temperatures. It has a peak near the transition. The solid line is lattice data, and model A and model B are here. And they don't look terribly impressive, I think, until you realize that this is a 0 parameter fit. There are no free parameters in these fits. Okay? So they both do a pretty good job of representing the physics of the pure gauge theory. Okay? Quarks work the same way, except it's 1 plus the Boltzmann factor times p, where the gauge theory it's 1 minus log of 1 minus. You know, you have to put it all together. And for example, with model A with massless quarks, what we do is we find the saddle points. We look for the saddle point of lowest action. Okay, since we're in the complex plane, we're really not entitled to ask, that it be a minimum of anything. It's just a saddle point. And we get some graphs like this. And what you see is, for example, that in this region of crossover, we're crossing over in temperature at various values of mu. You see that trace P, which is the solid line, is different from trace P dagger, precisely in this crossover region. Okay? So somehow the effects of PT are strongest in the transition region. And this shows two things. One is, these are contours of constant psi. This is the thing that is non-zero when PT symmetry is broken. And this is as a function of mu and t. Okay? And what you see is that the effect is strongest right where, keep doing that, things bend. And this plot over here shows for model A where the mass matrix has complex eigenvalues. Here at large mu, not too big t. Okay? What's surprising is that in this very simple model, that model B, although superficially somewhat similar in the behavior of psi, does not have complex eigenvalues of the mass matrix. So there's a strong difference between model A and model B here in how this works.
And the number denoting the contours, what do they mean?
Psi is an angle, so these are absolute numbers. These numbers here, since they're masses, they're actually in MeV, okay? They're actually in MeV. So these are a very small effect, in fact. Now, time is running short, so I'm going to skip ahead. I'm going to skip all this lovely stuff about heavy quarks, and I'm going to skip to the most complicated model and the most realistic model, which is the PNJL model, which includes all kinds of effects, including chiral symmetry, breaking, and restoration. So, again, if you know about NJL models, Nambu-Unilocini models, you know that there are 4 fermion models, and they mock up somehow the effects of QCD by causing chiral symmetry to break. And this is a pretty well-known technology, so I won't go into it in any detail, but that's what's done. Everything is set from 0 temperature physics, and when you look at the behavior of, just to take a random example, I'll look at fixed temperature varying mu, and what you're seeing, first of all, you're seeing trace P and trace P dagger at various values of the temperature, 50 MeV, 150 MeV, 210 MeV. But you're also seeing the behavior of the chiral autoparameter, which is starting off at some large value and going to a small value. So what you're seeing is the crossover in QCD from the hadron phase to the quark-gluon phase, okay? And we've done all this nice analysis for you. And the net effect is summarized in this plot. And so please wake up for this part, okay? Okay, so this is psi in the temperature versus mu plane. I'm using the quark mu rather than the baryon mu. Both conventions are used. So the location of the critical endpoint is right here around 300 MeV rather than about 900, which it would be if I were using baryon chemical potential, 3 times quark chemical potential. And what you see is that in model A, psi is non-zero. The biggest effect occurs as almost an outgrowth of the critical endpoint. This is the region where PT symmetry breaking effects are largest, right here. If I go to model B, the same thing is happening, right? So even though the overall behavior is non-universal, there does seem to be some association of PT symmetry breaking with the critical line, that's this blue line here, and the critical endpoint here. I don't really honestly have a great theoretical explanation for this, but it does seem to be true. Now, if you look at the behavior of the mass matrix and you say, okay, where are the mass eigenvalues purely real, and where do they form complex conjugate pairs? In one model, model A, you see that there is, in fact, an extended region that goes up. This was also seen with the massless quarks, okay? And it just continues on forever. We know that, okay? So in model A, there is this large region that is infinite, in fact, where, and we know the analytic asymptotic form of this line here, where PT symmetry is broken. But for model B, there is a much smaller finite region, and it just looks like some analytic continuation of the critical line, just like that. So there is a real difference between model A and model B, and that brings me to my final slide. So what we've seen is that finite density QCD has a generalized PT symmetry. It's CK. It tends to break in the crossover region, which is where the interesting physics happens, around the critical line and the critical endpoint. In that crossover region at finite chemical potential, trace P is different from trace P dagger, as it should be. When CK symmetry breaks, there are generally complex mass eigenvalues. There's one case where it doesn't happen, but that's kind of a pathological case, honestly. And that leads to oscillatory behavior in the color charge densities, because the Poliakoff loop mass is actually this Debye screening length, right? So if you say that it's got a complex part, what you're really saying is that there will be oscillations in color charge density correlation functions. The question is, of course, are those color charge density fluctuations experimentally observable? Because that would be really interesting. Because if you look back here, and if you look at the region that will be probed by CBM at FAIR, it's basically this region in here, okay? Okay, right in here. And so there's the potential of differentiating between model A and model B, for example, or some other model, right? We're agnostic about modeling in the face of experimental data, but still it's pretty interesting.
Conceivable that there will be oscillations if you have an analog of a vortex lattice in the, well, let's say the dual. But experimentally it's non-equilibrium physics. So it's very difficult. Now, my friend Apoorva Patel has suggested that it might be experimentally observable and has some papers describing it. But frankly, to get from Euclidean space correlation functions to non-equilibrium real-time behavior is pretty hard. I think more interestingly is that if current work on developing good algorithms for lattice simulations at finite chemical density, a finite chemical potential work out, then you could test these predictions against lattice simulation results. You don't necessarily have to see the oscillations, which may have very long periods. All you need to see is you need to see the real part of the eigenvalues of the mass matrix coming together and going apart, the familiar sign of PT symmetry breaking. And that should be pretty readily observable, but that's predicated on getting the lattice simulations to work. So that means that we have the possibility of discriminating between models of confinement, as well as having a new and better understanding of QCD at finite density. Okay, thanks.
So, questions, comments?
Two questions. First of all, the toy model by
Arts and Stamatescu?
Yeah. With the cosine theta minus I mu in the very beginning.
Yeah.
If I generalize it to say two-dimensional XY model, do you know any results? I just put the XY model with chemical potential.
Yeah.
So can you learn something?
Yeah.
It's the Higgs model. I mean, it's the abelian Higgs model essentially.
It's related. It depends on what dimension you're in. Yeah.
Two dimensions.
Yeah. So Pete Meisinger and I have a paper that you can find on the archive where we develop duality transformations for this class of models. And they're really interesting because the dual form is dual to things like anti-models, these models that have spatially modulated phases. So the dual form of these theories actually have spatially modulated ground states. It's pretty interesting and pretty rich. I don't know that generalizes to the non-abelian case, though.
Okay. And another question is not related directly to what you said, but you mentioned the sign problem. So is the people who worked, say, for example, on this complex Langevin
Yeah.
equation, is it the state of the art thing or the following Crowder and Parisi?
Okay, yeah, good. So there are two major approaches that I think have a hope. So one of the ideas, which I think is really actually a crappy idea, and I think Carl and just about everybody here will understand that. One of the ideas is to start here at mu equals 0 and do simulations and extrapolate out here. But it's pretty clear that the critical endpoint is going to ruin the convergence of any attempt to extrapolate out into the non-zero mu plane. So I don't think that's a very viable approach. So I think the two best approaches that are being worked on today are indeed the complex Langevin approach, which in some sense is an approach that's looking for complex saddle points, right? And the other approach, which is, actually I'd hoped that somebody was going to talk about it here. The other is the so-called Lefschetz-Thimble approach, okay? Which is based on a global analysis of the saddle points, an attempt to really find the saddle points in the complex plane and choose an appropriate contour through function space. It's a pretty ambitious program. My former graduate student, Hiramichi, actually has a paper with two Japanese colleagues that came out recently that tries to explore that a little bit.
And this somehow will tell lattice practitioners how to deal with the problem?
The calculation are meant, most of the calculation are done by expanding the chemical potential, calculating like 2 orders to the force or something like that, in which case, in the field, of course, in addition, so that you don't have the, you take imaginary chemical potential to avoid the sign problem. And then you try to make
Analytically.
to make an IT continuation, but that's there are limited results. Complex Langevin equation, I worked on it 20 years ago. It's a nightmare.
Actually,
Yeah,
Claude Bernard worked on it.
Claude Bernard worked on it in the context of yeah.
And he did it actually for 2 PT symmetric models. He used it to try to calculate the expectation value of phi in an IX cube theory and also a minus x to the 4th theory, and got really accurate results. Of course, those are just quantum mechanical models, so a lot easier.
Yeah,
But he was actually able to calculate expected phi.
yeah. I am optimistic in the long run, but not optimistic necessarily in the next couple of years. I think the group that is working most extensively on complex Langevin is really enthusiastic because they think they've solved a nasty numerical divergence problem where the trajectories tend to wander off into the complex plane and never come back.
That's one of the issues.
Yeah, that's one of the issues. But in fact, I think our fundamental physical and mathematical understanding is somewhat lacking. And this is sort of a beginning of trying to understanding what the real underlying physics of the problem is. That was part of the motivation for doing this phenomenology. Philip.
As a sort of side comment, you introduced the Nabuyon-Lacinio model. Now, ordinarily, it's not renormalizable.
It's not.
Now, however, the talk that I originally planned to give at this conference is one in which psi bar psi acquires an anomalous dimension, and it drops from dimension 3 to dimension 2 and becomes renormalizable.
That was the conference in Tel Aviv on Beyond the Standard Model that I was at 3 weeks ago. But yes, you're completely right.
I discussed this model in the large N unit.
Sure.
Like 20
Sure.
quarter
Sure.
century ago.
Oh, I did it
In the
40 years ago.
Huh?
I did it 40 years ago.
Yeah, but in the large N expansion, you can show that it looks very similar to a model in which you have a fundamental scale.
Yeah.
Yes, that's correct.
Yeah, I mean, there has been a lot of interest in this in the context of BSM physics. Not so much in this. Here, if I had a better model to do chiral symmetry breaking, I would use it. But it turns out that NJL models work
The people in Jena,
pretty well.
Ogilvie, they talk about asymptotic safety. They find even in the large M some fixed points which are non-perturbative. Which this model is normalized.
Yeah.
NJL
Yeah,
for minus epsilon.
Yeah,
Non-perturbative fixed point.
let me just say that in terms of finite temperature and density physics, that the NJL models are not are not universal, and the results are very cutoff dependent. And there are regions of the phase diagram where it's very difficult to extract much physical insight, particularly down around mu equals 300, t equals 0. Turns out to be a very difficult place for these models to give you information. So, don't take them too seriously, just a little seriously.
Okay, so are you going to grab the clay prize for the mascot?
Yeah, in just a minute. But Qinghai first.
I have a general question. One reason we use Euclidean time is we want e to the minus, we want e to the is become e to the minus s. Since now you got complex s already, why still bother with Euclidean time? Why go back to the real Minkowski time?
Oh, because it turns out that real-time finite temperature calculations are real hard. Yeah. I mean, there's a
Just
whole.
that they're very slowly converging if they converge.
Well, there's other problems as well. There is a formalism that might work, and it would be worth investigating. But there's a lot of technology to master, particularly for QCD to do real-time calculations. But I mean, we could.
Even quantum mechanics, a path integral in time. You're not going
Yeah,
to do it.
yeah. I mean, I should say, and it may be of interest to you, that the case of mu, which is really A4, mu not equal to 0, is not the only sign problem that you find in QCD. There's also interest in simulating the behavior of quarks and hadrons in Minkowski space electric fields, right? And that also has a sign problem for precisely the same reason. It's because you're taking something that's real in Minkowski space, and then you're analytically continuing it to Euclidean space and picking up an I. Yeah.
Any other discussion? Okay.
Okay.
I think maybe we should take 2 or 3 minutes just